Okay, it's Tuesday, 3:05 approximately in the afternoon. Hopefully some of you saw this on the website that I posted up yesterday. If you didn't see it, you're going to hear a lecture on it right now. And I'm holding on to some papers. So one of the things about being a student, and as you're walking in, hopefully everybody's going to catch on to this, is integrity and doing your own work. So when homework gets turned in and the grader detects direct copying, the same exact work on more than one paper, I mean there's multiple groups in this case that are involved, but that's not acceptable, plain and simple. So, and I know this happens in other classes, and this same lecture is probably given by other people, because I actually investigated this by talking with Dr. Trimboli, who has had most of you in class before. So faculty do talk, and we talk about students when we get people on a list, so we go over this. So I went over this with them. I can fight it, but I know fighting it I won't win. Cheaters don't prosper, though. They actually fail in life because they're not going to be able to do their own work. It's that simple. You have to do your own work, and you have to be accountable for it. So the reason why I give quizzes is because in the past I've actually had enough trouble with a variety of things along these same lines where I've actually said I just can't let homework be turned in because it can't be good for anything if people don't do their own work. And that includes scrounging up solutions from the internet, from the book, and those sorts of things. It's a temptation, right? It's actually a bad temptation to actually go do that. What you want to do is sit down and do your own work. Now, what you can do, though, is if you're sitting in a study group, you can talk about problems and talk about approaches and things, but what doesn't get you anywhere is to sit down and just somebody copies from somebody else, because that's definitely where the problems lie. You have to know what you're doing, and in the case of what was just identified by my grader, and I've been studying the problems before I came down to class, it's not a matter of necessarily getting it right, because somebody can copy from somebody else and they can make the same mistakes. That's certainly possible. So, but there is an intent there, I guess, just the same. So what am I to do? I'm doing what I'm doing. I can stop collecting homework, and last year people pled with me not to do that, and I kept it under control, or the class kept it under control, and I didn't have to take any measures. I'd like to be able to have problems turned in, because I'd like to have you be able to work problems with Python and the modeling tools. So I'm not going to not allow the next homework assignment to be turned in, but the microscope is going to stay tuned in to what's been going on. And unfortunately, it's just a few people, but you've heard the saying, a few bad apples spoil the whole bunch, or any of those other sayings that you may have heard your mother tell you. My mother's the one in my family that told all those things. Like, what was another one? If you can't say something nice, don't say anything at all. That's a famous one that I remember that I heard a lot when I was growing up, but that's not in regards to this incident. So what I'm going to do is I'll let you pick up your papers at the end of class. I'm going to hold on to the ones that I want to talk to people about. So if your paper is not in the stack, it means that I want to talk to you, okay? The other thing I want to talk about is what my plans are for Tuesday. Or Thursday's quiz. I'm going to go over the quiz because there were struggles on the quiz. I think everybody, according to the grader, there were just, maybe I was a little bit ahead of my time when you being prepared to work that theorem, but we'll talk through that, and that's kind of what I'm planning for Thursday's quiz. I do have a new assignment sheet up there that has got problems in it that finish off chapter 2 that we're in right now, and both of them involve using computer tools. One will be using Python, and the other one's using Wolfram's Alpha. And I'm going to talk about that today too. These are both really good problems to be working. The Alpha one is actually a really nice problem to work. It's a modified version of what's in the book. I just changed it around some. And the other one is on filter design and measuring group delay and gain and phase and that sort of stuff, and is based on examples that are already in the Chapter 2 Jupyter Notebook. So my intent today, now that I've gone through what I did, is to finish off this chapter and get ready to go into Chapter 3. I was going to get some dates out there, but I just got carried away or got engrossed in looking at these problem sets and pushing up some other stuff before I came to class. So the quiz solution that I put up there actually had some errors in it, and I re-pushed that up there, and I think it probably got graded with some things more lenient than, well, that was kind of the plan I had with the grader, but I think now I've got all the details in there, so we'll look at my detailed solution a little bit later. So does anybody have any questions on what I've just talked about or anything? Any suggestions? Some of you don't know anything about this. If you're a graduate student, you're saying, I don't even understand why this happens, but unfortunately it does. Yeah. My discussion with Dr. Trimboli, though, was somewhat revealing because he told me about even worse scenarios that he had in his class. So, where the good students were coming to him upset because of what was going on the other side of the equation, and that was not a comforting thing to hear. And some of you might be those people that actually went to him. I generally just stop letting homework be turned in. That's the simplest answer. But unfortunately, that's not totally satisfying to me. So I'm going to see what happens. Prosecuting is always an option too, but what does that do? Maybe it doesn't do anything. I don't know. Prosecuting, I mean, I can give you zeros and things like that, or go beyond that. So you're about ready to say something, but maybe you don't want to say anything.
I'm just hoping that you wouldn't,
do that.
Like, yeah, in fact, these, especially the homework problems that involve Jupyter notebooks are really, I kind of like that whole idea of a periodic, a Fourier transform or a periodic function really came out, and that last problem, the problem that we
you just turned in, yeah.
I mean, that was, I finally kind of got it.
Yeah, it's always available for you to play with, but if I give you something to do and you know you're getting something point-wise for it, I think it gives you more incentive, right?
Yeah, it does.
Well, it's just something to think about. It's not like I haven't been here before, so believe it or not, there used to be ample excuses for why code was verbatim and stuff like that, but that excuse kind of went away. It used to be that you could print for free in the computer labs, and the stories that I've heard was, oh, I found it in the garbage can, somebody threw it out. But that doesn't even work anymore because now it costs money every time you print a page, right? So I don't think there's a lot of trash up there that people could go scavenging through. I could tell a lot more stories, but I won't because it's just part of having been here too long. So we were talking about linear systems last time. We'll come back and look at that quiz. I think coming through the spectral analysis, which is what I'll make the quiz on Thursday, drill down on some more, and Fourier transforms, the periodic theorem and so on, is probably one of the bigger bumps in this chapter. So now we're kind of over it and we're moving forward, and we'll get into modulation theory, and I think that'll be pretty pleasant for most of the time. As a matter of fact, this class kind of has this kind of a on-ramp where we're coming through review, we have some little bumps and things, and then we're kind of almost totally flat, if not even coming back down again where it gets easier even for a while towards the end. So, you know, the 5 people that left this class, if this wasn't for them, that's fine. But sometimes you just got to have patience with yourself and your abilities and just push through it, and then you climb higher, and then you achieve, and then you go on from there, right? I'm just thinking about things that happen in life. I played in the Handbell Festival. I was telling you about that on Saturday. There's a woman next to me that I played next to for many years, and about 4 weeks ago she stepped down because she was seriously ill, and then she let everybody know that she was terminally ill, and her doctors thought that she would last through the end of February. Well, I found out, we played our concert on Saturday, and her empty spot was next to me, and I played a few of her bells and some of the pieces that I played on, just thinking it's kind of like a memorial for the fact that she can't play anymore and is not doing well. And I found out yesterday that, or Sunday afternoon, I guess, she passed away late Saturday night. So, you know, you get older and more people die around you that you're close to and spent time with, but it doesn't get any easier, I don't think. So it's kind of been, it's had an impact on me. So we all have things like that in our lives. So maybe that's what's got me a little bit down right now too. At any rate, moving into this linear systems review, filtering, and then some new topics come up in here, but they're not big showstopper things. We were talking about stability for LTI systems, and we have mostly linear time invariant filters, but there are nonlinear systems that we'll be dealing with, and those are also in this homework set. That's what one of the simulation problems is, or the problem for Wolfram Alpha. But this theorem right here gets used in some of the homework problems and is just a standard result for bounded input, bounded output stability. Remember, we talked about this last time, because this is the theorem that leads to the Fourier transform not having any singularities on the j omega axis and it existing, and then that's what leads to no poles on the j omega axis in the S-plane. And if you want it to be causal, furthermore, then all the poles have to be in the left side. Transfer function is just the Fourier transform of the impulse response. So here's the causality statement. One of the things that the book throws in here, which is kind of a new statement, I suspect, is this Paley-Wiener theorem, which states that not only does the energy in the impulse response have to be have energy less than infinity, then also there's this condition, this integral right here, which is just kind of intriguing, because when you first start learning about filters and you first start learning about the idea of a brick wall filter, an ideal filter, you think, that's what I want to build. And then you learn about digital filters in probably 3205, some in 2610, and then more in modern DSP and so on, is can't I build an ideal brick wall filter? Well, the answer is no. You can get very, very close. And this theorem kind of tells, in a way, what you can and cannot do. So if you just kind of dissect what this integral means, which is what, oops, get my pen working. Maybe it's got a new sheet. There we go. Statement 1 is, from that integral, you cannot have any interval of frequency where you have the frequency response equal to 0. So that is, just telling you that if you wanted to have a filter that had a stop band where it's just nothing gets through over an interval of frequencies, can't do it. But it does allow for isolated points. So this thing will work. You can have a pass band. I guess I should have tried to draw that a little bit flatter. You can have a pass band that's very, very flat, and then you can have a stop band where you have, just drawing that as 0 and 1, where you have zeros in the stop band at selected frequencies. You just can't go have an interval that you can integrate over, because that's going to be the natural log of the absolute value of 0, which is going to be the absolute value of that on top of it, which would be infinity, so that would blow up. And the roll-off rate can't be too great, but you can do polynomial types of roll-off rates, which is what you get in the practical filters like the Butterworth, Chebyshev, and elliptical, which I'm pretty sure you've covered in 3205, right? In my discussion with Dr. Trimboli, well, actually on Friday we did interviews. 4 of us were in a room for over 5 hours doing phone interviews, and it's myself, Dr. Trimboli, and Dr. Platt. We're on the search committee to hire another comm systems faculty member, so who will probably teach 3205 and some other things coming up next year, because Dr. Trimboli is the only one who's taught it for the past 7 years, and he goes on his first sabbatical next fall. It's history for you guys because you've taken it already, but we actually need somebody to teach it. So that's a candidate for the new faculty member. And everybody goes on sabbatical sometime. Dr. Song went on sabbatical, and I taught EMAG 1 for her, which was a fun class for me because that was my minor, but there's some people that always teach the same class. I don't always teach this class, but ever since 2 faculty members ago, when that person left, no one else has taught it because it just didn't happen the last go around. It was getting close, but never happened. So we were discussing in our phone interviews when somebody asked us what is in that class, talked about filters. So we have even symmetry if it's a real filter, in other words, real impulse response, and that's a Fourier transform property. We have spectral density relationships that the book talks about. We haven't really proven those because they're up in chapter 6 for the power spectrum, but for the energy spectral density, we already know that to be the case just because of the way you get at the output spectrum from the input. You convolve the impulse response with the input, and then if you take that to the frequency domain, you go to the Fourier transform, and you get the multiplication of the frequency responses. To make it work in the power spectral density takes a little bit more because you're working with autocorrelation properties, and we haven't gone into that. It's something that gets covered in COM 2 and also gets talked about in modern DSP when I teach that in the fall. But it makes sense, right? Input spectrum, magnitude squared of the filter, input energy spectrum, magnitude squared of the filter, so it shapes the spectrum. And this is an example that just kind of goes through a really simple circuit. Since everybody has programmed in C, you're familiar with the idea of the whole Hello World program, printf. This is the Hello World of electrical engineering, I think, the circuits, RC filter, right? You've seen it over and over again, but it's always good to play with it a little bit. I showed several different ways of solving it here. Differential equation is probably the least interesting, right? The one you really don't want to have to go to. Solving with complex impedances is pretty good. Probably the best one, though, is to go to the Laplace domain and just work with S and then make, and I didn't write that one in here, but just make this substitution when you get done. Does anybody have their favorite way? Pardon me? The S domain? Yeah. Take control systems next fall if you want to have the ride of Laplace domain, because that's what controls is heavily connected to. We're heavily connected to the frequency domain because that's what comm systems wants. So this is the RC low pass magnitude and phase. If I now, just to show you though that having theorems doesn't necessarily get you everything you want. So suppose I would like to take a rectangular pulse and send it through in the frequency domain. I can go ahead and take that to the frequency domain to get its spectrum, and then I can multiply those if I want to get the inverse Fourier transform and go that route. But that doesn't always work for everything you might want to do. In this case, it works fairly well because you can, at least I think, actually this, I'm trying to think, do I have an example here where I show that's not the case? I guess in this case I worked it in, I did the convolution directly. I didn't go to the frequency domain. So I took and got the frequency domain result by just multiplying the Fourier transforms, and then I got the time domain result by just convolving. Because there's something about multiplying a sinc function by some other function and then having to inverse Fourier transform that. In other words, if you have to do this and go back to inverse Fourier transform, you get y of t. There's something that's unattractive about that. And what I'm getting at is the sinc function is not really a very attractive thing to have to integrate because it's got a singularity in it. You know, sinc of x is sine x over x. What do you remember about calculus is you have all those singular integrals that you work on when you take calculus, those special cases to integrate. So it's not a really fun function to have to integrate. Getting the response in the time domain from a direct convolution, though, is not too bad. And you can get that from just convolving a step and a delayed step and then subtracting them. I think there was a homework problem that dealt with that a little bit, but it was also worked in example 218 here of the notes, so just convolving them directly. This was just kind of as a review, though, to show what happens between time and frequency domain and the inverse spreading idea. So when RC gets to be large compared to the pulse width, then you lose a lot of fidelity in the input pulse. And then you go over and look in the frequency domain, and as a result of that loss of fidelity, because RC being large, the cutoff frequency is tiny, so the spectrum gets really compressed as a result of the low cutoff frequency. Conversely, if the time constant is small, then the pulse goes through with high fidelity and the output spectrum is wide again. And in this case, down here, you can see that the main lobe is almost perfectly intact and the side lobes have just been clipped down a little bit, which is, you know, totally the opposite of what went on up here, where the main lobe has been totally mutilated, right? The 2t corresponds to this, so that's the green, and the 10t over 10 corresponds to this, which is the wideband filtering scenario. So visualizing that the RC low-pass filter is just constricting things more and more. This is the statement I already made. I think I had this in the notes twice, just showing that you can get the spectrum at the output from the magnitude squared of the input spectrum. Then there's another collection of results here that just says you have a periodic input going through an LTI system, and the output will be periodic in steady state. And you can get then the Fourier coefficients by just multiplying by the magnitude and phase times the input Fourier coefficients at those individual frequencies. This again assumes steady state, but that is the nature of Fourier analysis, because what's special about Fourier, everything starts at minus infinity, right? That's the way it comes up by the definition. So if a periodic input is driven into a system, you assume it's been applied since minus infinity. Or you just apply it at zero and wait a certain number of cycles for the transients to die out, and then it's in steady state as well. Okay, that's kind of the review topics. Now some of the newer topics are starting right here. So I'll pause and see if anybody has any questions on what I've just gone through. We will be using filters in modeling and simulation in the projects that come up, and those filters will always be digital filters just because we'll be doing discrete time simulation. And we'll use LFilter, which is Python's version of filter that you have in MATLAB. So get used to doing that sort of thing sooner than later. The first project is actually going to get assigned here probably in 2 weeks, I think, is when it will come out. And it will be due before spring break. So if I was looking forward on the calendar, '22nd is when's the last day before spring break. So I'm going to guess the project will probably be due on the 15th, and the first exam is going to be within first exam will be along about the same time. So let's see, the first is a week from this Friday. First exam could be either in this week or the 12th, something like that. That's just kind of an approximation. I have to look at my schedule, but it's generally after I get a little through linear modulation and have gone back to look at the Hilbert transform in Chapter 2 as we needed in Chapter 3. So it's coming up fairly soon. Question?
Practice exam?
Yeah, I will. There will be 2 practice old exams, last year's and the year before, that'll be up there. And does anybody else have any questions? I know there's one person going out of town, if I remember right, who told me they were going to be gone on a trip. Maybe there's 2 people.
Yeah, me.
How soon would you be willing to post this?
Probably beginning of next week. I mean, it's just getting around to it. You know what my main theme is? Writing labs. I'm just spending most of my free time doing that, which, free time is just a fictional thing, right? There's no such thing as free time, I don't think. If it's not that, maybe, I'm doing dishes or cleaning or something, That's the arrangement you have when you're married, right? If your wife cooks, the husband has to do the dishes, or vice versa. At least that's the way my household works, which is how I grew up too. I have a son at home, so he has to participate in cleaning up too. I'm just saying, that's your free time, right? Doing things like that. Or shoveling snow, that's a novelty, right? You don't get to do that very often. So I'm thinking about it, and they'll get up there and you'll see them. Okay, and new topics are distortionless transmission. I think it probably gets mentioned in 3205, but I'm not sure how much. I don't know. Does it? It's not a topic in there. Okay, so we have filters, but what do filters do to systems? Do they introduce distortion? And that's what this topic is about. So a distortionless system would be this example right here. So what we're allowed to tolerate and still call the system distortionless is a gain scale H0 and a possible time delay T0. So I brought in my fiber, and let's see. Since I'm on my microphone, if somebody wants to grab this, yeah, it is dangling off of here. Somebody want to come up and take it and maybe slide that end in underneath this tape or something. It is glass, so it's not like plastic fishing line that you might think. It's actually made out of glass. So that's single mode fiber, and it was the discovery or the creation of single mode fiber that changed things drastically in optical communications, guided wave optical communications. When I was first in industry working on an IR&D down at Motorola Government Electronics in Scottsdale. Okay, pass it around. Maybe break that piece off, I don't know. See how strong it is. See if you can snap it. I worked with graded index optical fiber, which was what was called multimode fiber. So when you put laser light through the fiber, because of the sheathing, and this is actually in your EMAG book, so 3110, which some of you are taking now and some of you already had, right? There's a discussion of fiber optic in there, but fiber optic cables, but the nature of a multimode fiber is when you try to send light at a given wavelength down through the fiber, it doesn't propagate all at the same velocity. So you have some bands of frequencies or optical light frequencies propagate faster and some propagate slower. So you get what's called dispersion, which takes optical pulses then, which are being sent to carry ones and zeros, and smears them out so they get dispersed. It was the invention of single mode fiber, which can propagate a single mode of laser light without any dispersion free, which means pulses can be sent very, very fast, or at gigabits per second, and that was the discovery that was made quite a while ago. And one fiber can actually carry multiple channels because you can carry multiple wavelengths. So you can have like 4 different colors of light, not red, green, blue, yellow, but frequencies that correspond to different colors of red, infrared, typically infrared. So it's approximately distortionless, which is simply amazing because coax cable, any other medium we can think of, has got some dispersion in it. It also has attenuation. The single mode fiber doesn't have very much attenuation either, so it can go a great distance. When I worked with it in the lab, though, I had this big spool that was all sheathed up, so it was a kilometer's worth of fiber, and that's what I had for the testing that I did on this high-speed data, and I attempted to send 1 gigabit per second through the fiber using an infrared laser, semiconductor laser. And it's because I was involved with a free space optical system that used green laser light that took some of the ideas of the electronics and applied those to infrared laser diodes, and did some experiments with some of our breadboard hardware that we had left over from the system that was delivered down to White Sands Missile Range. It's been a long time. I just remember having fun doing it. The photodetector was an avalanche photodiode that had to have a bias voltage of about 90 volts on it to make it function as an avalanching device. And an avalanching device means one photon hits the detector surface and then it dislodges multiple photoelectrons, so it has gain associated with it. But I had to have a power supply, and that power supply, or battery, I don't remember how I did it. All I know is I got shocked multiple times. I accidentally was leaning on something and my fingers went on the bias supply for the avalanche photodetector and I got zapped. It didn't throw me on the floor, it's just that intense tingling feeling that your body tells you pull back, because has anybody ever gotten buzzed from a power cord accidentally? You know what it's like then, right? It's that kind of buzzing feeling. Hopefully you don't do it between here so it goes across your chest, but if you're pulling a cord out or something, you might slip your finger on there and get that on your hand, right?
Feel numb for about 5 minutes afterwards.
Well, it depends on how bad it is, I guess. 90 volts is not that bad, but it is a tingling feeling. And they always tell you, though, that you may not die of the shock, but you might die of the reaction, because you might pull back and rip something really bad in your body because you're reacting very quickly. So that's an example of distortionless. And then if you take the Fourier transform of this system, it's just a pure delay. So the pure delay just has that same gain and then a linear phase. So phase shift linearly ramps with frequency. So what are the distortion types that are the complement to this would be amplitude is not constant over a band of frequencies. Phase is not linear over a band of frequencies. or out and out the system is nonlinear. So the system looks like, say, a polynomial response. So you put in a signal, and instead of getting the signal out, which would be this term, something proportional to that, you get out a bias term, and then you also get out, say, a square law term or cube law or something like that. And that's what one of the homework problems deals with. Getting back to these first two, though, and then thinking of filters, when I first learned about distortionless systems, I thought, well, if a system's good for anything, I want a filter. I want to remove a signal not of interest and keep a signal of interest. So in the business of military communications, they have this terminology SOI and SNOI, signal of interest, signal not of interest, and they pronounce them as SOI and SNOI. Just to let you know, that's, everybody makes up an acronym, so that's what I learned a long time ago. So if a filter is going to pass a signal of interest and reject a signal not of interest, that's definitely distortion, but then you have to stop and think, what does that really mean? Well, it's over the band of interest that you're talking about it being constant. So it's perfectly okay for it to reject a signal. It's just in the band of interest, you'd like to have it flat. And in the band of interest, you'd like to have the phase flat. So we'll come back to that. There's an example up here in the notes right here that comes out of the book, which I call a fictitious system because it's just sort of to drill home the concepts. It's the type of thing that makes for a good quiz question to just identify what frequency bands are distortionless and which bands are not distortionless. But before we do that, we'll go on to group and phase delay. So group delay, which was in lab 1, just to get your feet on the ground with seeing it, but now is showing up in this next homework, is defined as minus the derivative of the phase response. And then there's a scale factor of 2 pi in there, and that's because theta is in radians and group delay has units of seconds. So you just want to remember that the units of group delay are seconds or microseconds, nanoseconds, whatever. So the 1 over 2 pi converts it back to time again after you take the derivative. So for a distortionless system like the one we were just talking about right over here, this one has the angle of h equaling minus 2 pi f t naught. So it's just got a fixed delay of t naught seconds. So now if you take the derivative of that minus the derivative of that with respect to f and divide by 2 pi, which is what I did right here, you get exactly t naught seconds. So that's the group delay in that ideal distortionless system. So it just says all frequency bands that pass through that system pick up the same amount of delay. So the way group delay makes sense, and the term group delay is, what do you think of when you think of group? You think of more than one, don't you? Is that true? You don't say a group of just me went somewhere. That's contradicting. So it is a group, and that refers to a group of frequencies. So it's the delay associated with 2 or more frequency components, or the delay that they undergo in passing through an LTI system. So if we say the group delay at F1 does not equal the group delay at F2, and both of those frequencies are in the band of interest, then we know that there's delay distortion in the system. Just like in the optical fiber, if 2 different wavelengths of light that constitute the message spectrum that's being sent down through the fiber pick up different amounts of delay, then the pulses will get smeared when they arrive at the receiver, and then that limits the bandwidth or the data rate that you can send through the fiber. So if all components pick up the same delay, then everything's good. Does that make sense? And I can jump right down here to a practical example. This is right out of the transmission line theory chapter in the EMAG book, right? 3110. I really love the fact that that book teaches you about transmission lines right from the get-go. The detailed fields and wave stuff that you do later in that class tend to get lost in the muddle because it gets to be really hairy stuff with vector calculus and everything, but transmission line theory is extremely practical for essentially every EE because it's so important. A high-speed PCB for computers, for RF, for just baseband analog. When you get things running at a high enough clock rate or high enough frequencies, then you have to think about the interconnects on the board as being pieces of transmission line, and then you want to make sure that you keep the reflections down. In this case, this model assumes the reflections are zero because there's a matched source impedance and a matched load impedance. And all that the ideal lossless line then generates for the signal is the propagation delay, which is the length of line in meters divided by the velocity propagation in meters per second, which, like in coax cable with its epsilon R, epsilon relative permittivity, it usually works out to be about 2/3 the speed of light. Does that ring a bell with anybody? It just depends on the dielectric material, but it's around 2/3. So that's acceptable because an ideal lossless line doesn't attenuate at all and applies uniform time delays to all frequency bands. A real transmission line, though, has loss because there's loss in the dielectric and there's loss in the copper or whatever the conductor is made out of. So it will attenuate at higher frequencies, and then that's going to do what? Introduce amplitude distortion. It's not going to be flat. But over a band of interest, it might be approximately flat, like within a fraction of a dB, and you'd say it's good. It's approximately distortionless. I just like to use that as a kind of a practical example of something that is distortionless. So this goes into a little bit more discussion, then this leads into the definition of phase delay, which I'm not particularly excited about. It doesn't really, I don't value it the same as I do group delay. But if you pass a single frequency component through an LTI system, it's always going to appear distortionless at a single frequency because, and this is something, as I recall, you learn in 2610, like really early on. You look at a sinusoid and you look at the phase of the sinusoid and then you relate that to the time delay. Remember doing that? So from that standpoint, it looks distortionless because it's just a pure time delay at a given frequency. And so that leads to the definition of phase delay is just dividing the phase by the negative of 2 pi times f. And that's because that's the conversion that you go through here to get time in seconds back again. So the phase delay for a distortionless system is again just T naught. But if the system has got a non-constant group delay, then the phase delay is not going to be able to pick that up because of the way it's defined. It doesn't have the same value. And when you spec things, I just don't see people speccing things in terms of phase delay. They always go for group delay. I mean, when I worked at RT Logic over 10 years ago now on a SATCOM project, I was modeling some filters for a high fidelity simulation that were filters that existed in satellite transponders, and they were waveguide filters, but they were filters that had been compensated to have essentially constant group delay in the passband. Their group delay was something, I'm just sort of remembering this vaguely from the data that I worked with. I don't think it did that. Get rid of what I wanted to keep. So over the band of interest, it was a ripple of plus and minus so many microseconds or something, and then outside of that band, it went off in a hurry, but it was at least flat over a band. So it was a compensated filter, and this was a SATCOM link that was going to send really high-speed data through it. I think it was 8 PSK or something that was sending through it, and if you don't have constant group delay and a digital data waveform, you mangle it up pretty good so the bits cannot be recognized so well, and then you make more errors than you would if it was constant group delay. So what else was I going to say about that group delay? So you build compensators, and in that case they were waveguide filters. I really don't know what they looked like. It was just specs that I had. It was a system it was a NASA system, so it was a NASA satellite or NASA transponder, I think. Yeah, I'm pretty sure that's what that was. All I know is I had very detailed math models that they had given me to work with for the simulation. This is sort of a, like I say here, a fictitious system, but it's trying to get the point across that what bands of frequencies do we have distortion free? Do we have amplitude alone? Do we have phase, group delay, phase delay, types of distortion? So the green area that I've got shaded in there is where there's no distortion, because you look at the amplitude response, it's constant. You look at the phase, it's linear. So this is constant in the green band, linear. And then the group delay will be constant in that band as well. So in most scenarios, group delay and phase shift as a function of frequency kind of go hand in hand, and they're obtained from one another. One's the derivative of the other. So if phase is linear, then group delay will be constant. So generally, what people specify in systems, they'll specify these two. Gain is flat within a fraction of a dB, and the group delay is flat within microseconds or nanoseconds or something over a desired band. So most people care in comm systems about speccing those two. That's what you see. Has anybody seen that in any systems you might be involved with as an intern or something? Called out somewhere? So when you widen beyond this band, if you try to go greater than plus and minus 10 hertz in this fictitious example, now you're going to introduce amplitude. And so if you go to the limits of where group delay is constant, which is about 15, so that's at 15 and minus 15. Group delay, again, this is a fictitious system, so I don't understand how the system's group delay could be constant when the amplitude response would change suddenly. That's why it's called a fictitious system, but it's just applying the definitions. Group delay is flat between plus and minus 15, but amplitude is not flat. So I would, if I was to ask the question, what type of distortion is present if you want to operate with a band of interest between minus 15 and plus 15, or just call it the low-pass band with 0 to 15 hertz, you would say amplitude distortion is present. Group delay, good to go. If you then widen this out to go up to 20, just call it low-pass again, 0 to 20, then you've got both group delay distortion present and amplitude distortion present. And I realize phase delay is in here too, but I'm just not wanting to concentrate on that one, but it's no longer constant as well when you get wider than 15. But does that sound reasonable? This is fictitious though, so the real filters are what really matter. The bullets here just kind of go through some of the discussion. Before we get into some realizable filters, we're going to now just take a more detailed look at nonlinear distortion. And this is, we're going to look at an instantaneous nonlinearity. So there's no memory, or also known as memoryless. So it's a power series model, just saying that the output is the input with various scale factors on the powers of the input. So a second order nonlinearity is the example considered at this point. So you have an a1 x of t, and then you have an a2 times x squared of t. And a typical thing that people talk about when they're looking at the degrees of nonlinearity, and now let me just stop for a second because I'm going to guess that in electronic circuits this topic has come up at some point, right? You have the small signal modeling like for devices and amplifiers and things. You generally don't spend any time on anything but the small signal linear model. Is that true or not so? Because I'm just remembering, I taught electronics too when I was a graduate student a few times. Actually, that's how I got into teaching. A guy had to have triple bypass surgery and they needed a replacement really fast, so they said, you know electronics because you came from Motorola Government Electronics. I was a board level designer, so they dropped me in about a month's period. They said, will you do this? And I taught 3 sections of electronics 2 at Missouri S&T, which had like 5 sections of everything running every semester. It was just huge. I still don't believe that I came through a program, at least I was at a school that was that big, but you guys wouldn't know what to do if you had 5 sections to choose from, would you? I gave my exams in the evening because that's the way that school operated, and I gave my exam, a common exam that everybody came and took it in a big classroom in the evenings because I had 3 sections of one class, 3 of the same topic. So a common test is the two-tone test, so that's what this is called. So put in 2 sinusoidal tones and then see what happens with the nonlinearity. What sort of action do you get? And so when you go through the trig expansion for this, you have the linear term, which is, this is the linear term. Then the square term. Linear term is what you want. And A1 is going to be fairly large, and see, I have a typo in here. I should say A2. So typically A1 is much greater than A2, but we're still caring about what A2 is going to do. How many dB down are the distortion terms going to be, and what sort of impacts are they going to have? So you have to square out that sum of 2 cosines, and when that squares out, you get a DC term, you get 2 second harmonic terms, and then you get sum and difference terms. Usually the DC term is not that something that people talk about, because in most amplifier applications that are involving radio signals, the DC bias generated would not necessarily be a big painful issue, but it still could be. The most significant terms are the cosine terms. So what we've got coming out now are 5 or 6 different terms. So we've got the input frequencies, then we've got the second harmonic of the input frequencies, and then we have these terms here which are called intermods. And intermod terms involve sums and differences of the input terms. And right now with this second order nonlinearity, the intermod terms are in general not as harmful as higher order intermod terms could be. So I've got a picture on the next page of the spectral orientation, but if you were listening to music through an audio amplifier though, and you brought in two strong signals and the two signals were close to put the signal close to the saturation point, then generating the second harmonic terms would be called harmonic distortion. And then the terms that are the sums and differences are called the intermodulation distortion. Both of those are bad from an audio high fidelity standpoint because you would hear them and it would make music and the chord structure of music, which is generally pleasant sounding, it would make it start sounding harsh and unpleasant. Now, distortion effects on guitars and things are done on purpose, but I'm talking about in addition to what somebody intentionally wanted to have happen. In a radio frequency system now, the intermod terms and the harmonic terms might actually now start landing at a location that's going to cause some serious issues for the rest of the signal processing in either a transmitter or receiver. So here is a spectral picture of just an input, a single frequency, and showing the DC, the fundamental, and then the second harmonic that gets generated. When you put in two tones, though, now you get these other terms that come out. You get the intermod terms, and then you get the harmonic distortion terms. Still not all that bad because they are separated from each other. When we go up to the next level, when we go to third order nonlinearity, in other words, if we were to think about, and this is what the homework problem has in it, so that's why I'm kind of building up to that point, then we get some bad things that can happen when you get to the third order, because when you get to the third order, you get sums and differences involving three frequencies, and if the frequencies are roughly close to each other, then one of those intermod products is going to land pretty much right in the same band as one of your desired signal would be. Is that, I know you're not fully grasping that, but can you see that if some distortion term ends up landing really close to where you care, then you're going to be upset because it's going to be interference and you're going to actually hear it, or it's going to show up and get demodulated somehow or another. If it's far enough away, a filter that would select out things like that would hopefully get rid of those. But when you get to the third order and the fifth order and the seventh order, all the odd ordered nonlinearities produce intermod terms that land inside the band. And that's what the RF system designer people use their software tools to try to figure out how bad it's going to be and where's it going to hit, try to figure that out. Those of you in the comm lab are going to get a chance to see a little bit of that going on with the mixers. I've been working with the board yesterday and today. Things are working really, to me it's awesomely impressive. It works really nice. I mean, good and bad things. Bad things that I expect to see are happening, and good things that I expect to see are happening. It's just things that happen because mixers involve nonlinearities, and we'll give more of a drill down on mixers in chapter 3. Before I jump to Wolfram Alpha and look at the homework problem, I'll just say that if you had a continuous spectrum and chose to model it, a signal with a continuous spectrum, and then put that into, say, this second order nonlinearity, linear plus second order, then you can bring in your multiplication theorem, which says you convolve in the frequency domain. So here, you're not just looking at the individual spectral lines that come as a result of the nonlinearities, but now you're actually going to get a whole continuum of junk that comes out. So in this case, if it's a rectangular spectrum corresponding to the signal of interest, then you'll convolve it with itself and that'll produce a triangle. So you get this kind of a setup right here, where you've got this triangle which is broader than the original signal, that's spreading, broader in frequency, that's now going to be sitting there along with your signal of interest. Now presumably that triangle is way down in amplitude relative to the signal of interest, but it's putting these intermodulation and harmonic terms as a continuous distribution of frequency all throughout that spectral band. You can look at ideal filters, but before we do that, I'm just going to jump over to his homework problem. This is 262. And 262 says take these two signals, x of t, and just consider what happens when you go through a cubic nonlinearity. So it's going to dispense with a1 times x of t, a2 times x of t squared, and a3 times x of t cubed, and it's just going to focus on, can't draw on that, it's going to focus on the cube of x of t as the sum of those two signals. So I'm just going to take a more exotic example, and then I'm not going to do the analysis on it, but I'm going to just show you. This is Wolfram Alpha. Has anybody in here never used alpha before? You used Mathematica before?
20 years ago.
Okay. Well, you don't have to know much about Mathematica to use this. You just have to be able to type reasonably good mathematics. So I'm just giving you the hint. So I'm going to say expand, and so what I'm going to do is I'm going to say expand. Actually, Mathematica likes square brackets for its functions, so that's officially a function name. So I'm going to expand cosine of f1 plus cosine of f2, and then I'm just going to use the hat symbol since that's popular in a lot of calculators and things for the power. And so I'm going to take it to the third. Well, I'm going to let you do that. I'm going to take this to the fifth power, close that off, and hit enter. And it's going to go to work down here, expanding it. But we're looking for a particular form, and that's what makes alpha pretty nice. It works a little bit longer. That form is not too cool. It's beautiful. I mean, a lot of math there. And Python has SymPy for symbolics, but I can tell you the form we're looking for. Can you see from what I've got on the screen which one would look like what we were just looking at? Would have harmonics and intermods. Okay, the one that has the 1/16 in front of it. This guy right here. That's exactly what you want. And what I want you to do when you work the problem is do a symbolic solution where you put in f1 and f2. So that way, if you put in two frequencies that you couldn't distinguish whether they were harmonics, like 2 times 1 would be 2, but 1 plus 1 would also be 2. But what you need to do for this problem is quantify them, whether they're harmonics distortion terms or intermod terms. Make sense? So when you use symbols, you'll be able to break them apart. So this is beautiful right here, because you can identify what all those terms are. The coefficients tell you the strength of those intermod terms, and we didn't put any we just had a unit coefficient out there, but you can see you've got all these harmonic terms and then the intermod terms. So where are the harmonic terms? They're down below here. There's an F1, 3F1, 5F1, F2, 3F2, 5F2. You expect all those kind of intuitively with a trig expansion. But then you've got these various other terms that involve products of F1 and F2 added and subtracted from each other. And the frequencies, think of them as being the absolute value of these frequencies, because you know if you had a line spectra, you'd have a component at a negative and a positive. So just think of putting the absolute value sign around like F1 minus 4F2, because that's the way it would work, right? From the line spectra, it'd be on the positive and the negative simultaneously. So that's what you do in that problem. It's very straightforward. Sit down, every one of you, and just do this. It's easy and it's kind of entertaining because you're using a tool that's pretty powerful, unless you want to do the expansion yourself. I don't think you want to. Even with a cube, it's got enough terms in it that, and it's a particular form that you just don't think of, right? We want it in this form here because then you can identify where they're coming from. The RF systems engineers have tools that are like spreadsheet tools that will give all of these intermod components, and then it will give all the coefficients. So the software is written, it's out there. You could go probably download something for free and get a specific intermod tool. But I don't know, I think it's more fun to use Wolfram Mathematica, or Wolfram Alpha, I mean, because it's kind of like I'm just sticking with the basics. I haven't tried to figure out a specific tool, but an RF systems engineer would want all the strengths of the coefficients, and then they would get a picture of where they lie, and then they would have some idea where things might happen. A guy that I worked for here in town at Paracle Communications does a lot of outdoor measurement stuff, and one of the things he taught me when I first started working with him is that you can have a rusty bolt on a bracket on an antenna that's on a tower somewhere or another, and if two transmit antennas are really close to each other, they will generate enough power that due to that rusty bolt, you'll create what's called passive intermodulation. So third order and fifth order passive intermodulation, what goes on with these higher orders is that if you have two of one frequency and then one of another frequency, so if F1 and F2 are pretty close to each other but yet they're separated, 2 times F1 minus F2 will land almost right on top of F1 and F2. It will just kind of land in that same general region. So the thing that he dealt with this passive intermod was up in Denver typically. He had scenarios he told me about where, say, the fire department is on one and ambulance is on another band, and they're close and they're on the same towers, that the rusty bolt would come along and cause these passive intermods, and these public services they were jamming themselves just because of some artifact on the antenna. We're not metal alloy specialists. That's more of a mechanical engineering thing, but it's kind of disappointing to know that just the tightness of a bolt and how corroded it is actually was causing problems that he had to go deal with. I don't think he climbed the tower. I think a professional that gets paid for that acrobatic high wire stuff, they get paid a premium, right, if they're going to climb a tower usually, because they could fall and kill themselves. They probably had to go up there and replace something. He just used his Field Fox or something like that on the ground and made measurements of what he was seeing as intermods. You'd have to wait for the two transmitters to be up at the same time and then be looking on the spectrum to see all of a sudden an intermod term would pop up right in that same neighborhood. And that's what he explained to me. It's a good story, and I believe it. I didn't get involved with that. I did the other stuff that I think I told you about with drive testing at a certain time of the day. I told that story in here, right? Where we thought there was a rogue cell phone out there that had gone wacko and wasn't being able to be power controlled, and it happened at morning rush hour and at lunchtime rush hour. So it was up in Denver, way in North Denver. And sure enough, it happened, but I was up in the rooftop of a building in the penthouse with a spectrum analyzer looking at what was coming up into the base station from the various users out there in the network, and we were trying to catch things, and I don't think it was a rogue cell phone, one that had gone bad. I think in the end it was just simply the network was too cluttered up, and it was the power control algorithm was malfunctioning, and that's how it happened. But they're wondering, why is one user so strong and kind of wiping out other users on the network? None of us have control of that, right? Our cell phones do that automatically. They're commanded to do that. But the thought was that somebody had hacked their phone, and they had basically turned up the power on their phone, so it was always going to punch through the clutter and get the call up without, having a privilege or something like that. I don't know if that's a privilege, though. Your battery would run down faster. But I went along with it. I was on a sabbatical, and I got paid to do that, basically sit on the rooftop like that. Okay, the next topic is ideal filters, and we'll be using ideal filters almost exclusively in Chapter 3 and in Chapter 4. So the ideal filter is just fictitious brick wall filter, but it's just good for the preliminary analysis. So if you're going to come up with an ideal low pass, high pass, band pass, and then band stop, just make it a distortionless filter. Notice it has a flat pass band, and it has linear phase in the pass band, high pass the same way, band pass the same way, and if you needed a band stop, you could do the same thing. You might say, is that reasonable? Well, my argument for doing that is that if you can't design a system in block diagram form, a concept with ideal filters, and have it work, why would you expect, if that doesn't work, why would it work any better with non-ideal filters, right? So you have to start somewhere. So you start with something that's very easy to work with and model mathematically. And then you would take it to the next level, like, okay, now if I put a realizable filter in here, does something get destroyed, or are the tolerances a lot tighter? So you first sketch out ideas with the ideal filters, and that's pretty much the mainstay of Chapter 3. And there's relationships. I mean, low pass and band pass are related, for example, through frequency translation. That's one way of getting at it. That's this example here, how to take the impulse response of a low pass, multiply it times a cosine, and that is going to shift it up to be a band pass filter. And that's just, there's the impulse response of the low pass, and the impulse response of the high pass is that, and I could punch that into the Jupyter Notebook very, very easily. So with the time left, I need to go look at the old quiz, and I was going to show you a few more things in the Jupyter Notebook, but I don't think I may not get time to do that. So this is the quiz, and I've got to get those papers out to you too as you're leaving. So periodic signal, I said Fourier transform the first period, not a problem. Time is in microseconds though, so you have to be aware of that. Fourier transform now P of t using the known theorems, and what we're going to get out of here are some quantities that do have microseconds in their units. So when I originally solved this, I did not include this term just because it was a scale factor. I didn't really get excited about it, and I don't think the grader actually, I think he ignored it on your solution. So, but it should be there technically, and it's going to resolve something in Part C. But I think that worked fairly well by everybody, because that's just direct application of Fourier transform pairs. Now when you want to do the spectrum of the periodic signal, you have to put up what I have in red right here, which is taking and sampling the spectrum of a single pulse or a single period, and then locating those spectral lines with the delta function at multiples of the period, which I called it T naught here, but you can call it T naught in the math, same as TS in the theorem. So that's 20 microseconds. So the fundamental is going to be 1 over that, which is 50 kilohertz. Tennis quit working momentarily. So you put that out in front, and now you have to sample P of F with F replaced by NFS. So I make those substitutions. And then I also carry forward the 10 to the minus 6 for the microsecond units I had from the beginning. But then I have this 50 times 10 to the 3, or 50 kilohertz, that's out in front. So ultimately, I brought those two together and brought the scale factor down to 50 times 10 to the minus 3. Again, that didn't get graded because the grader, I didn't put that on my original solution, so that got slipped over. But it's a scale factor, and I guess it has to be there because if the energy is going to get spread out in frequency as a result of doing this transform, it has to get squashed down, because the whole area, or the whole energy, if you integrate the magnitude squared of the Fourier transform, that has to, or in this case, the power of the delta function through Parseval's theorem, that has to be conserved, right? You can't get more power just because you make it periodic. The power is associated with one period through the theorem. But at any rate, the spectral lines are going to be at multiples of the fundamental, which is the 50 kilohertz. Last problem, I think, was pretty straightforward. That was the only problem that jumped into the power spectral density. So the time is now up, but I want to just say, what am I going to make the quiz on Thursday? The quiz is going to be my idea, unless somebody says they want to get tested on something even harder. My idea is to have a repeat of using this theorem. So it'll be using the theorem that I have in the red box. And you have my permission to take your crib sheet and write that theorem on there from the notes, because it's not on there, right? I didn't put it on there, but you can write it on your crib sheet. You're going to have a handwritten crib sheet when you take the exam, so just modify your crib sheet and put that on there. It's a blue boxed equation, right? That occurs earlier in the notes. I'd write the one that's the blue boxed equation, because that has the time domain, and then it has the two-sided arrow, and then it has the frequency domain. So that'll be one problem. And then the second problem is going to be something from power spectral density. It won't be a simple integrate the power spectrum. It will be given some sinusoids, get the power spectral density, and or get the autocorrelation function for a couple of sinusoids, or some permutation of that. Start with the autocorrelation, get me the power spectrum, then sketch the power spectrum. I mean, I'm just going to think, what are the various permutations, and I don't know what it's going to be right now, but it's going to be something along those lines, and that's what the homework problems were that you didn't turn in. They were that type of thing. There's drill problems in the book, and then there's homework problems, so there's other problems to look at. Key result is when you get the autocorrelation of a sinusoidal signal, whether it's a sine or a cosine, it's always going to be a cosine in the autocorrelation, because remember, autocorrelation is phase blind. That's the term that I used in the notes. It doesn't matter if it's sine at an angle 45 degrees or cosine at an angle minus 10 degrees. It still comes out to be cosine of just the frequency, and tau is for the autocorrelation. And the spectral lines, again, don't have any phase, and they're just the a squared over 2 are the amplitude, or the power in a sinusoid, and then the spectral lines is a squared over 4 on either side. So I think there's some fairly good rubrics there that are, things you can commit to memory from looking at the examples and see, yep, this is the way it works. So that's my plan. I've got the papers. I wanted to go through some Jupyter Notebook stuff, but I'll do that. Some other stuff. I was going to show you the cross-correlation. I never showed that to you, right? Like take one signal and delay it from the other, like the GPS application, and cross-correlate it, and sure enough, the correlation peak is shifted in time. And I just wanted to prove that to you. And I'll also talk more about the filter design stuff that's in the Jupyter Notebook. But we're out of time. I'm going to put the problems up here, and if you don't have time to get it right now, I'll have them next time.